So here's the basics of what you need to know about the periodic table for this unit test. The periodic table is organized into periods or rows and groups or families, which are columns. For this unit, we're focused primarily on the groups, the families. So in this very first group over here, you have the alkali metals starting with element number 3 with lithium. Hydrogen, sitting right above lithium, is actually a nonmetal, but because it also forms an ion with a +1 charge like the rest of the alkali metals, it sits there. So our first group is called the alkali metals. Our second group is called the alkaline earth metals. In the middle, in groups 3 through 12, we have what are called the transition metals. Then below the periodic table, we have the inner transition metals. Then over here, underneath this heavy black staircase, we have some other metals, gallium and germanium, indium, tin, antimony, thallium, lead, bismuth, and aluminum. This heavy black line here that you see here, this stair step, is what separates our metals on the left side of the periodic table from our nonmetals, which are on the right. On the stair step, I have these stars here. These stars represent a group called the metalloids. The metalloids have properties of metals and nonmetals, and that's why they're in the middle. They have properties of both. When we look at our elements, they're organized into energy levels, and their electrons have these energy levels in order to be organized. Quick review here from physical science. In the center of the atom, you have what's called the nucleus. And the nucleus has hot protons, which have a positive charge, and neutrons, which have no charge. Outside of the nucleus is what's called the electron cloud. And in the electron cloud, we have negatively charged particles called electrons. Those electrons are organized into energy levels. Energy levels close to the nucleus, and then they get farther and farther away. The last energy level is called the valence shell. And these are the electrons that are gained to make negative ions. These are where the electrons are that will be given away to form positive ions, and electrons that will be shared are here as well. And that's to form what we call covalent compounds. And we talked about covalent compounds, but I'll get to more to that later. So the number of valence electrons determines how many electrons are going to be lost and gained and what ions they'll form. Well, here's what you need to know. Metals lose electrons. Metals are going to lose electrons, and so their ions are going to be positive. So metals only form positive ions. Nonmetals will take away electrons, they will gain electrons. Nonmetals gain electrons, and so they form negative ions. So your metals are positive ions because they lose, and nonmetals are negative ions because they gain. So when we look at our periodic table, I have some numbers written in red. You'll notice that everything to the left of the staircase is a positive number, and everything to the right of the staircase is a negative number. So your group 1 metals form a +1 charge. Your group 2 metals form a +2 charge. The transition metals form positive ions, but they can form lots of different ones, so we don't have to memorize anything there, except for 2. That would be silver, which is always +1, zinc, which is always +2, and then we have aluminum, which is always +3. Then if you imagine a mirror that happens right here. So we have +1, we have a +2, and then we have a +3. Then on the flip side of the mirror, we have -3, -2, and then -1. So all of group 15 forms a -3 charge. All of group 16 forms a -2 charge. And then all of group 17 forms a -1 charge. Our noble gases, which sit over here in group 18, they form no charge. They do not form ions. So it's +1, +2, silver 1, zinc 2, aluminum 3, -3, -2, -1. So let's talk about naming ions. We call positive ions cations, and cations are all of our metals plus the polyatomic ammonium. Now there's a phrase I haven't mentioned yet, polyatomic. Ions are of two kinds. Ions are either monatomic, that means it's an element on the periodic table, or they are polyatomic. The polyatomic ions are more than one element bonded together that have a charge. They act as a unit. So our positive ions are cations, and that's all of our metals plus the polyatomic ion ammonium. And we call our negative ions anions, and that is all of our nonmetals and the rest of the polyatomic ions. Positive ions are always going to get their full name when you name them. And there are three types. We have our group 1, group 2, silver, zinc, and aluminum ions. Those are our monatomics. Their names don't change at all. Then we have our transition metals. Transition metals get their full name, plus you put the charge in Roman numerals. For example, if I have iron that has a 2+ charge, then I would call that iron Roman numeral 2. Or say, for example, I had tin with a 4 plus charge, then that would be called tin 4. And then we have ammonium, which is just ammonium. And you know ammonium is NH4 plus 1. Our negative ions may change their name. If they are monatomic, that means they're on the periodic table. Then we change the ending to IDE. For example, fluorine which would be F -1 becomes fluoride. Oxygen, which is O with a 2 negative charge, becomes oxide. The polyatomic ions get their full name. So let's look at our chart of polyatomic ions. You'll notice that a lot of these polyatomic ions end in ATE. You'll notice that most of these polyatomics end in ATE. When you see ATE or ITE at the end of a name, that is a clue to you that our polyatomic ion has an oxygen in it. When you have the A to E, like see here, phosphate has O4, phosphite would be PO3. See, nitrate is NO3, nitrite is NO2. There was a mnemonic that I taught in class to remember the 8 ions, most of these, and it was Nick the camel ate a clam supper in Phoenix. N stood for nitrogen. We know that these are the 8 ions. So the next element after N would be O. The number of consonants tells you how many oxygens. So NCK means NO3, and the number of vowels tells us how the charge. So that'd be NO3 -1. So then the C in camel stands for carbon. There are 1, 2, 3 consonants, so it's CO3 for carbonate. There are 1, 2 vowels, so this is a -2 charge. So clam, chlorine, chlorate, 3 consonants, ClO3, A for -1. Supper would be sulfate. There's 4 consonants and 2 vowels, so sulfate is a -2. Phoenix, of course, talking about phosphate. There's 4 consonants, 3 vowels, so that's phosphate. So if I want nitrite, I would write NO2-. If I wanted chlorite, I'd write ClO2-. Sulfite would be SO3, 2-, and phosphite would be PO3, 3-. I also made a Quizlet to help you memorize these anions. But that's not the main thing that we're going to do with these. The main thing that we're going to do with these is we're going to write chemical formulas. So let's look at how we could put these two elements together. How we could put opposite charges together and then make a compound. Let's say I wanted to make a compound between calcium and oxygen. Calcium, we find it here in group 2. So it has a +2 charge. Oxygen, we find it over here in group 16. It has a -2 charge. Whenever we write an ionic compound formula, the overall charge is 0. So since my charge for calcium is +2 and my charge for oxygen is -2, I have the same amount of positive and negative, so I can write the chemical formula as CaO. Now let's write another one. What would I get if I took calcium, which is a +2, and paired it with fluorine, which is a -1? Well, now let's look at what my breakdown of charges is. I have +2 on this side, and I have -1 on my negative side. Those aren't equal. The only way I could balance this out would be to multiply my -1 by 2. If I multiply -1 times 2, that equals -2. So I would have a +2 charge, a -2 charge, and my charges will equal. And the way we show that is by giving fluorine a subscript of 2. So now I have CaF2. And that is my chemical formula. Let's try another one. What if I wanted to bond sodium with phosphorus? Sodium is in group 1. That means it has a +1 charge. The phosphide ion is in group 15, so it has a charge of -3. So 1 and -3. What do I have to multiply 1 by in order to get it equal to -3? I would have to multiply 1 by 3. So if I had 3 sodiums for every 1 phosphate, then I would have 3 positive charges and 1 negative charge. Well, look what that does. In essence, I took the number 1 and I wrote it here. And I took the number 3 and I wrote it there in order to get Na3P. We call this the crisscross method. Let's do one more like this. One more simple one. One more binary one. What if I have barium? Barium has a +2 charge, and I want to bond it with nitrogen. Nitrogen has a -3 charge. Well, here's where that crisscross method is going to come in handy. I could take the 3 from the nitrogen and write it here. And I could take the 2 from the barium and write it here. And make my chemical formula Ba3N2. So what have I done here? If I have 3 +2 charges, 3 times 2 is a +6. And if I have 2 -3 charges, 2 times -3 is a -6. And so since my positive and negative charge is equal, I know that I've written the correct chemical formula. So how would I name these? These have only main group elements. So when I write the name for this compound, I always list the metal first, and Ca is calcium. Start typing. Ca, there we go, is calcium. And then the O is oxygen. It's a monatomic anion, so I have to change the ending to IDE. And we would call that calcium oxide. This calcium and fluorine compound down here would be calcium fluoride. This compound over here with sodium and phosphorus is going to be sodium phosphide or phosphoride. And then down here with the barium compound, what I have would be barium nitride. Let's do some practice with our polyatomic ions. Let's take acetate and let's bond acetate and see what happens when we bond acetate. So acetate is C2H3O2 minus 1. What happens if I bond acetate with zinc? Zinc is a 2 positive. Acetate is a negative 1. So you know from our last examples that I would need to take this 2 and I need to bring it over here. Well, as written, it looks like I have C2H3O22. So how do I avoid that from happening? By putting my polyatomic ion in parentheses. Because I don't need 22 oxygens. I need 2 acetates. So when I write the chemical formula, I write it as this. CN C2H3O2, close the parentheses, Roman numeral 2. And what if I wanted to use ammonium and carbonate? Ammonium is NH4 plus 1. Carbonate is CO3 negative 2. So plus 1, negative 2, I need to have 2 NH4s. So my chemical formula for ammonium carbonate would be NH4 2 CO3. And I would call this ammonium carbonate. Roman numerals are key when you're working with the polyatomic ions. What about this compound? What would you name this compound? The first thing you want to do is locate the metal on the periodic table. This metal is Mn. Mn is right here. It is smack dab in the middle of my transition metals. So that tells me I'm going to need a Roman numeral. This is manganese, and I need a Roman numeral. Well, I need to figure out what that Roman numeral is. Then Roman numeral stands for the charge. So how do I know what the charge is? Well, if you have to look at your anion, my anion is chlorine. Chlorine has a -1 charge, and there's 2 of them. So that means the overall negative charge is 2. Since there's only 1 manganese, that 1 manganese has to equal that -2, which means this is manganese 2, and then chlorine is a monatomic ion, so I need to write its name out and change its ending to IDE. So this becomes manganese 2 chloride. Hope this clarifies a lot for you and helps you write those formulas and write those chemical compounds for ionic compounds. Stay tuned for my next video, which is going to be all about covalent.